Very often in first year chemistry, you're taught that there's 5 general types of reactions: synthesis and decomposition, single replacement, double replacement, and combustion. In reality, at least for practical purposes in inorganic chemistry, there's only 2 types of reactions, and those are oxidation-reduction reactions, or redox reactions, and double replacement reactions. The key distinction there is for oxidation-reduction reactions, there's a change in oxidation states. In double replacement, you just have ions switching places. So if we look at our oxidation-reduction reactions, this is a situation where there's some transfer of electrons that results in a change in oxidation states. Right? So the key there, as we were looking at ways the chemical reactions can take place, we have breaking or forming chemical bonds, and we have a transfer of electrons. In this case, there's some transfer of electrons resulting in a change in oxidation state. And you may have heard of oxidation states before when you're doing nomenclature, and you're talking about transition metals that may have multiple possible oxidation states, like copper may be a +1 or a +2, or silver only has a +1, that kind of thing. And then you have to assign a Roman numeral in those names to specify what their oxidation state is. So you've heard of oxidation states before, and now we need to assign them, right? And we need to assign them not just to transition metals, but to everything. We'll abbreviate oxidation states or oxidation numbers as OX, number sign or whatever. That's not a super legit abbreviation, but it's good enough for our purposes. And it's important that if we're going to look at this, we define what is an oxidation state for our purposes. And again, if you have an ion, its oxidation state is its charge. If you have something that's not an ion in a compound, the oxidation state is what its charge would be. Okay, so let's write those out. The oxidation state is what the charge on an atom in a compound would be if it was an ion. What the charge on an atom in a compound would be if it was an ion. And those words are a little overwhelming. It's like, what the charge would be if, but it isn't. In a covalent compound, within, you don't have this exchange of electrons, you have the share of electrons, and they aren't ions. But the way that the electrons are shared can treat things or make things act as if they were ions. An analogy I've used in class is like if you have some athlete, maybe a soccer player, and then you say, well, you play football. And they don't play football. But if you did play football, what would be your position, right? We can make a conclusion there that allows us to predict how they would behave under those circumstances, right? So it's a soccer player, but if he were a football player, he would have this position and he would behave this way. So in our oxidation states, it's if it was an ion, it would have this equivalent charge and it would behave this way. So that's the basis of our oxidation states, and the reason we need to keep track of them is they're going to give us an idea of what is oxidized and what is reduced in a redox equation. So let's take a look at the idea of oxidation and the idea of reduction for those purposes. When I think about those two terms, you can memorize to yourself, well, oxidation is an increase in oxidation state, or you can go with your instincts, which say reduction is going down. You are reducing something. So in reduction, you have a decrease in the oxidation state of something. And let's write that out right now. And reduction in a redox situation is a decrease in the oxidation state. All right? And how do you get a decrease in oxidation state? Well, we've done ions before. And when atoms give away electrons, they become cations. They have fewer negative charges. You're losing negatives. And when atoms gain electrons, they become ions. So how do you get a decrease in oxidation number? You lose some electrons, or sorry, you accept some electrons. So for reduction, there's a decrease in oxidation number. Electrons are gained, right? And we might change that terminology. They are accepted from, and we'll sneak in some terminology in a different color here, they're accepted from the the reducing agent. I'm going to try one more time. Yes, reducing agent. All right, and that's terminology that we're going to have to address later, but for right now, it's a bit of foreshadowing. The electrons are gained. You're getting them from somewhere, and that's the basis of redox. If something somewhere is going to gain electrons, something somewhere has to provide electrons, okay? You have to have both things happening. An example of a redox situation, something real simple, might be like chlorine gas gaining 2 electrons and turning into 2 chloride ions. All right? The oxidation state here is a 0. The oxidation state here is a -1. It has gone from 0 to -1, which is a decrease. The chlorine has been reduced, right? That's how that works. So terminology that is a bit of a stumbling block, but if you can think of it in opposites, we can label things this way. The reduced species is the oxidizing agent. Okay. If you look here, we just said reducing agent, and down here we're talking about oxidizing agent, and we're pairing that up with reduced. So I think if we can just right off the bat get it out of the way that we have this mental reverse taking place for the same species. The thing that gets reduced oxidizes something else. It causes something else to be oxidized. Well, what does reduction mean? It means its oxidation state goes down. How does the oxidation state go down? It gains electrons. The thing that is oxidized has an increase in oxidation state. How does it get an increase in oxidation state? It gives away electrons, right? So by accepting electrons, the reducing agent causes something else to oxidize, right? And so that's that relationship and that naming scheme for how that works. So we'll sneak in here, just to match our terminology, oxidation. And again, I don't explicitly memorize that oxidation is an increase in oxidation state. If I can remember reduction, then by process of elimination, I can get reduction, or so I can get oxidation. So oxidation, if we just match all of these terms, it's an increase in the oxidation number, right? And it's a situation where electrons are given away or electrons are lost. Electrons are donated, right? They're given where? To the oxidizing agent. All right, sorry, it's getting a little sloppy there. If we look at a simple example like aluminum metal will accept or will give away 3 electrons, and you end up with Al3+ and those 3 electrons. Just like here, we went from an oxidation state of 0 in its elemental state to an oxidation state of 1-. 0 to 1- is a decrease. 0 to 3+ is an increase. It's an oxidation taking place. And this produces those electrons, which then reduce this. So we can use that same terminology and say that the oxidized species is the reducing agent, right? The oxidized species is the reducing agent. Okay? And I wanted all of this on the board at once so we can look here once again and say, this gives up electrons, it is oxidized, these electrons are accepted, it is reduced. This causes this to be reduced, this accepting those electrons causes this to be oxidized. And so, again, an easy way to remember it is that there are opposites paired up. Species that is reduced is oxidized, is the oxidizing agent. Oxidized species is the reducing agent. So if we're going to look at this terminology, and if we're going to use this terminology for electrochemistry and other settings, we're going to need to be able to assign oxidation numbers to things that aren't ions, all right? So these are ionic species. Their oxidation number is the charge, right? They're on the football team, like my previous analogy. What happens for covalent compounds, and how are we going to deal with that? So I'm going to split that into a separate video